The following program is brought to you by Caltech.
Okay, so the last speaker of this workshop is Jamie Bock from Caltech, and he will tell us about reflection on BICEP2.
Okay, thank you. I wasn't sure what I was going to say here at the end. I'm not going to say much about dust. We already talked about that yesterday morning. And I'm certainly not going to provide my own modest musings on inflation to this crowd. So what I'm going to talk about a bit, what I can contribute here is just to describe how the experiment was put together and what it really takes to build such a machine and the people involved. And at the end, I'll talk a little bit about what the future looks like from the experimental side. So this is our collaboration, and I know you see a bunch of people and a bunch of logos, but I see the faces and the individual people who are involved in this. And you know, a lot of students will tell you they're interested in cosmology, but if you ask how many students are willing to put 10 years of their life or more, whatever, into a project with no real hope of success, the list gets a lot smaller. And so these folks are real heroes, and I wanted to talk a bit about how our postdocs and graduate students contributed. And here they are. These are our postdocs. Some of these guys are from Caltech. So Jeff, you heard, and Martin Luker, and Roger. Walt was here, and Angela was here, and then and Zach, and graduate students. Grant's here in the audience, and then Randall and Justice graduated fairly recently. And then in terms of the history of the program, you know, BICEP was really conceived as a dedicated experiment to go after the inflationary gravitational wave signal. And that really came about because we were down the hall from Mark Kaminkowski. And so we got interested in doing this stuff way before anybody else did. So we conceived this machine as a unique instrument to do that particular job. And we always imagined that we were going to upgrade it in stages. The experiment was really designed for this stage from the beginning, but the detectors weren't ready. And we designed the detectors so that we could do the later stage as well. So you may not have heard about the predecessor to BICEP. It was called the Pullet Ron. And the Pullet Ron was, I guess, our way of learning how to do polarization measurements. And it had a fairly baroque structure. Had a single feed here with an orthomode transducer, which is a thing in waveguide which splits unpolarized light into two polarizations, kind of in plumbing. And it goes to two detectors with a series of back-to-back feeds, just one pixel in the sky. And it was going to go out here at Overo on, I guess that's the 5.5 meter dish. And Overo is not a particularly good site. And really the process of putting the Politron together, but we were really excited about going after gravitational waves. So we came up with this project as a way of getting our feet wet. And then because we're going to be out at Overo and you calculate, it's going to take like 5 years to detect anything, this all had to be mechanically cooled, and the lesson of building it was not to build it. The other thing that was happening at the time is that when I came down to JPL and Caltech, I was working on bolometers, these Spiderweb bolometers that look like this. So these are freestanding structures made in a microlab, and it's a micro machine membrane. So the thickness of the film here, this device is about 5 millimeters across, but the film that's standing out there in free space is just 1 micron thick. And so these were pretty successful. We dreamed this up for a balloon experiment called Boomerang because we were worried about cosmic rays coming and interacting with the detector. And this mesh is our millimeter wave absorber, but if we spiderweb out the mesh, we can reduce that. It turns out this is a good idea for other reasons, and it also turns out that our calculation of the cosmic ray rate for the pull was way too pessimistic. Anyways. So this came down to JPL in 94. But what had been going on at JPL long before that, in fact, going back to the early 80s, was a completely different approach, which is to make detectors for coherent detection. These are devices that were really started, I guess, with Rick Leduc and Tom Phillips at Caltech, and then Jonas Zimidzenis when he came to Caltech in 1990. And so these devices use antennas to couple radiation to a detector, and then using pretty fancy superconducting materials. This niobium titanium nitride allowed detectors to go up to the terahertz range, and these were really designed for Herschel, for far infrared astronomy, for an instrument called HiFi, and so they flew on HiFi. Whereas the spiderwebs were for more bolometric detection. They started in the CMB. Interestingly enough, they also flew on Herschel on a different instrument. But these two approaches and these two groups really didn't talk to each other for years and years. And then in 1999, we could see the direction, the need for more detectors for doing polarimetry. And Jonas Zimidzenis inspired us to get together. So this is a proposal that we put in 1999 with a really bad acronym called Kam Wah. And the idea was to basically combine the two technologies. We're going to use bolometers, which turn radiation into heat, with all the coherent techniques and antennas that have been developed by the superconductivity group at JPL. And so our focal plane was a very ambitious and futuristic, so futuristic we haven't realized it still, approach where we would get all the colors simultaneously out of a flat focal plane. And so the idea is you have a whole bunch of antennas and you can combine the radiation coherently with low loss microstrip, and you can form pixels on short wavelengths in little patches, and then by somehow magically combining with lots of crossovers, et cetera, you can make the next frequency have a bigger patch, and then the next frequency have a really big patch. And so in that way you can get out all the colors, and you can make diffraction limited beams, and you can get polarization, although this was just one single polarization. In fact, the truth is we haven't figured out really how to make this work in practice, as I mentioned. And we still haven't figured out really how to get out all the colors and all the polarizations simultaneously. The field has some ideas now on how to do that, but it's still a challenge. So this was visionary. The end of this was not very visionary. This was a semiconducting thermometer stuck on the end by hand because we didn't really quite trust the superconducting detectors. Also in this proposal features our goal. We were swinging for the fences. We were going to make a focal plane that had 1 microkelvin root seconds to get down to an R level of 10 to the minus 3. 1999. That's what we're going to do. I think this would take 64 Keck arrays to get down to 1 microkelvin root seconds. So it's still a challenge. But we were really motivated by this exciting quest. And then in 2001, Brian, who was a postdoc working on the Pullet Ron, and I were thinking that the Pullet Ron was not really a good way to do this. And we knew how to build a more capable system. And we wanted to have a system that would be compatible with the new detectors. But we knew the new detectors were kind of vaporware, and we wanted to build this in stages. So the idea we came up with was this compact telescope, because you don't need a lot of resolution, but you do need to have a lot of detectors, a lot of field of view, of course, because the detectors themselves, I should have mentioned, the detectors are limited by photon noise. And the detectors that we built for Planck are pretty close to being limited by photon noise on the microwave background itself. So you have to build more detectors. So what you need is an instrument with a huge focal plane, and you don't need a huge telescope. And of course, you want to control the illumination of the detectors and the systematics associated with the telescope. So putting this little telescope, putting it in a liquid helium cryostat meant that we didn't have to worry too much if the detectors see off the edge of the primary lens, and we can rotate the whole system about its bore site, which is ideal for polarization. And we can stick an absorbing baffle up at the top to catch any spillover that might go to the ground. So it seemed like a good approach. And then when the new detectors were ready, and we wrote this in the proposal in 2000, although we misused the word antenna, the new detectors were designed to basically go right in, because they'd look straight up. And the primary mirror, the image of the primary mirror as these detectors see it, is often infinity. So the detectors can look straight up, perfectly designed. And in fact, when they eventually did come along, we never changed the optics, so this basic structure. We had the first polarized spiderweb bolometer picture in this proposal. The first device is always ugly. Here's a piece of silicon nitride frame that's stuck to the devices, but we didn't care because they were working. And then we never took a picture of any of the ones after it, so we're stuck with this picture of a crummy one. And then we realized that this is going to be hard. Here's our sensitivity for an R of 0.5 curve. It's not so great. But the basic parameters of the experiment haven't really changed. We're going to do 400 square degrees of sky. We already identified going to the South Pole. We're going to have 50 feed horns, which is exactly what we did. And the sensitivities are a little optimistic, but not by much. And we're going to do 100 and 150 gigahertz. That's exactly what we did. We identified going down to the pole, and this is a little calculation or a cartoon, I guess, that Eric Yvonne made of what the polarized sky would look like. I don't know what the color stretch is on that. But this is all scalar polarization. And Mark Kamikowski and Eric made a nice plot here which showed our projected sensitivity. I don't know what R level this was here with BICEP2. And then we had our sister experiment, then called Quest, now called Quad, out at higher angular scales to do the scalar polarization. So that early theory advice was really helpful. We knew also from people like Wayne and Matthias that we should be careful, because there was this paper about leakage with a big beam experiment that would couple little imperfections in the matching of our beams to temperature anisotropies. And so with the small experiment, this was going to be our big challenge, because the temperature anisotropies are going off the top of the page here, but they're bright and they have a lot of gradients. And so with a big beam, we would be right at the peak of the temperature anisotropies. But I guess we decided to ignore that advice, and we plunged ahead. So then Andrew Lang got involved, and he loved this quest. This is his figure. He always called it a wild goose chase. And I somehow managed to motivate funding agencies to support us by gleefully calling it a wild goose chase. I would send him emails like, we're going to have this review, no geese, please. And pretty quick, after Andrew got involved, we would have meetings that looked like this. Huge number of people. You can see early on, we've got groups from Spider and people from JPL and John Kovac in the room, Bill Jones, Xiaolin Kuo. This would, I guess, would have been around 2003. Oh, Clem, there he is, back there. And so, very quickly we had a big team of dedicated, really excited individuals. This is an early picture made by one of the graduate students of our team, and I love how she's changed the lettering here. So we have bicep and put the phone, telecom phone, and our receiver and so forth hidden in an oscilloscope hidden in here. So we started building BICEP, and once we had the receiver, we were ready to go down to the South Pole. And at the South Pole, our instrument goes into the roof of the dark sector lab. It turns out that one of the keys of operating an experiment at the South Pole is not to put the experiment outside, it's to put it inside. And this was something that the DAISY experiment had figured out, and about a decade or so of other experiments had learned the hard way. So in fact, this is our telescope mount getting dropped in down through the roof. And the telescope lives inside the nice room temperature environment. And the nose, just the nose of the telescope sticks out into the Antarctic environment with a weather seal. There's an articulating Gore-Tex weather seal down here, which then connects the telescope and closes up the room. So there's a really nice approach. That exact same green weather seal was found on the DAISY mount, which Clem developed, and we shamelessly copied it. And the pole's an amazing place. There's all, these guys are the crew of 10 people whose job it is to unload airplanes at the pole. And during the summer, there's about 200 people at the pole keeping the place running, and their stated job is to run science. And if you look around, you're one of the science projects that all these folks are working on. And if you give them some free T-shirts, they'll do great things. And so these are the guys who basically delivered the hardware and installed our telescope. We're very thankful for that. Here's our little team. Again, we're inside the building looking up. The mount of the telescope is sitting up here on a platform. The elevation drive and the instrument itself is kind of up here halfway into the ceiling. And right now we don't have the weather seal on, so you can see light shining down from the outside, but that'd be closed up in the winter. And then our first winter rover was Denny Bearcats, who is a postdoc. And this is the last plane out from the South Pole. So you can tell by the long shadows. So Denny is now trapped at the pole from about February 15th to at least October, probably November. So that's a pretty big commitment. And in fact, many people on our team have wintered over either before or after this. Cynthia here wintered over for SBT during her postdoc just because she thought it would be fun. Here's what the sky looks like, of course, in the winter. And it's nice because we don't have the conditions are very, very stable. We don't have the turbulence associated with diurnal variations that you get at mid-latitudes. And so the conditions have been really great. Now, one of the things we wanted to do was we wanted to make life easy on our winter rover. and so the whole system is designed for really maximum efficiency. Our instrument runs, I'd say 80 or 90% efficiency just in terms of raw time on the sky, which is really excellent. And Denis' job was harder because we were using a liquid cryogenic system. And nowadays, we've even gotten rid of that. So I know their lives aren't easy, but we're trying to make them as easy as possible. Our next step was to replace the old detectors with the new ones. And I've mentioned this before, but this really was a radical transformation, going from feed horn coupled individual devices in BICEP1 to planar antenna arrays, so that the functionality of all this with the feeds that control the light the detectors see, individual filters and bolometers is basically all done on a single piece of silicon. And in fact, this single silicon wafer has the capability of 2 of these focal planes. The JPL Micro Devices Lab is really key to having this. There aren't many places in the world where you can come up with a new idea and actually build it. And then once you've built one of them, you can actually use this facility to make arrays of detectors. And bear in mind, this is a government lab. We're making arrays of detectors whose sole function is to look at the early universe and don't have very many other specific applications. And that's really remarkable, I think. Here's what the full focal plane looks like. These are 4 tiles because that's as big a wafer as we can build at the microlab. And each of these squares approximately is a pixel. They're about 4 wavelengths across, so they're 8 millimeters on a side. And so just the wavelength and the throughput you get, you're left with, we're basically using all the throughput in the telescope, and you have to make 4 wafers to do that. These wire bonds here are how we read out all the detectors, and these are the squid amplifiers that convert the tiny currents from the sensors, the bolometers, into a magnetic field that's then measured by a quantum interference device. So having a multiplexer here that works at 250 millikelvin is really a key to having a large number of detectors. We didn't have that before. And that was done by Kent Irwin at NIST. And then many of our postdocs, but I'll mention Martin in particular, were key to putting these focal planes, very delicate focal planes, together and testing them, and then pulling them apart and changing things and testing them over and over and over again. But once this focal plane was ready, and it was by no means clear it was going to be ready in time for BICEP2, it was time to take it back down to the South Pole. And here's Caltech graduate student Justice Brevik with the BICEP2 focal plane, getting in one of these ski-equipped LC-130 flying garages to go to the pole. And actually, he's leaving here from the edge of the continent. It's about a 3-hour plane flight to go to the pole. Short flight, but you wouldn't want to walk. And here's the instrument going together in the lab. You see all these very concerned people looking up and me looking down. That's kind of one of the delicate stages of putting the telescope together into the cryogenic system. Before we did that, we have to carefully clean the instrument. There's a picture of John Kovac, professor of physics, doing something to clean the instrument, and our tech, who knows better, watching him. Here's BICEP2 going into the telescope mount. This is going up a rail system that we built. The cryostat weighed about 800 pounds, I think, so it's a bit hard to carry for one person, being winched up into the telescope. And one of the remarkable things is both BICEP1 and BICEP2, we didn't really go and take apart the instruments very much. They basically ran pretty much continuously. Also note the large hammers. And then during the summer, this is what life is like. We calibrate the instruments. So this is a big campaign where all of our team comes down and we go through a whole battery of tests. It was just calibration after calibration, measuring the time response, measuring the spectral response. And this is a way for us to measure the beams. Here, the telescope is looking up on a flat mirror that goes off and heads off towards another building where our source is. Another nice thing about a small telescope is we don't have to, our beam's not that far, the far field is not that far. It's about 50 meters. So we can carefully measure our beams with a source that's, in this case, about 200 meters away. We don't need to go further than that. There were definitely some subtleties here. One of them was that there's some excess noise associated with the detector. And a factor of √2 or so degradation in the detector performance is really a bummer. You don't want to have that happen. And so we were scratching our heads, even during the first season, about what was going on and how we could deal with that. One of the difficulties here is that the multiplexer, which samples multiple detectors in time sequence, can alias this excess noise into our signal band. So the blue line is kind of the bump from the detectors. They can sometimes have this bump, and then the black line is what happens with the multiplexing. So it's really kind of nasty because you have a higher noise level than you otherwise would from the detector. So Jeff and well, largely Jeff, but also Justice worked really hard to figure out a way to improve this. And so it's a combination of going a bit faster and optimizing the bias. And it made a big difference. Here's our instantaneous sensitivity in the first year. And there's this notable step. And that step, and then another step here, those steps come from understanding this behavior and squeezing out all the sensitivity. And there's a big difference between the sensitivity we got here, about 16, what we had here, 24. It might not seem like a big number, but you square that, and that's how much time you have to wait. Time is not a quantity that works on a log scale, especially if it's your time. So that was a big improvement. And I mentioned here how efficient our observations were. This is the total observing time. You can see these dips here in the summer while we're calibrating, and then our sensitivity chugging on down to 87 microkelvin. While BICEP2 was in the field, we were still trying to figure out how to improve the detectors. One of the issues was our detectors early detectors had actually a fair amount of polarization mismatch. This is a plot of our vertical polarized detector minus our horizontal polarized detector, and they don't match. They give you this kind of Pepsi symbol because they're shifted. And Roger, one of our postdocs, calls them cross-eyed antennas because they're not quite looking at the same spot. This isn't a big effect, but we're really sensitive to it, so it's important. And Roger basically debugged what the heck was happening here that causes this systematic effect. And you can see the improvement from the early design, which, by the way, is in BICEP2, the blue stuff, and a later focal plane that's really improved. It was not a simple thing. Some of it had to do with the way light goes to the antennas, and some of it has to do with the materials. And separating that out and really understanding it was really critical. Another thing that happened is our optical efficiency got worse for a painful amount of time, about a year. And we went from having propagation, so this is loss in our antennas, how much loss you get per centimeter of length before and after. And once again, losing a factor of 2 really is not pleasant. And what was going on, we didn't understand. And really, Zach and Grant, with the guys at MDL, went through many focal planes to finally understand that this was largely a materials issue, and a surprising one. It seems to be properties in the superconducting niobium in our antennas, which was not what we were expecting. We thought that was going to be totally negligible, and it is, unless you have a problem with the fabrication process that you didn't expect. So that was also huge. Then this business about little beam mismatches causing big polarization artifacts. Because of this cross-eyed antenna effect, we are more sensitive to this than we were in BICEP1. and you can see how serious it was. If we don't make any correction, the level of residual systematic from temperature is this green line, and the dash red line is R of, I guess, 0.2, yes. So this effect would be big. And so Randall and John Kovac figured out a way to basically, you take the temperature map and you can make a template for what the beam mismatch, how that would convert temperature to a polarization signal. And so for every detector, you can measure that template. And you lose a couple of modes for that detector, and you can choose how many things you want to put in the template fits. There's a whole family of these beam mismatches going from a gain difference to a pointing difference to a beam width difference to an ellipticity difference. And if you do that, there's a dramatic improvement in the leakage. And we believe we're down here somewhere after doing all these measurements. And we can rigorously test them by looking at all of our difference maps. So this was huge. We would have been stuck if it hadn't been for someone like Randall. Another big development was how we handle the mixing from E modes into B modes. So there's a mixing effect from having a cut sky, and this was worked out by people like Kendrick Smith. But there's also a mixing effect just by how you scan the sky. So we filter because we have to deal with the atmosphere, and that's not accounted for in these fixes. And our team, because it's a big team, we have to have a certain level of discipline in terms of how we analyze the data. So the students, by and large, work on the pipeline. And the pipeline is the standard agreed way we do analysis. And if you're developing some new thing, you're off the pipeline and maybe ignored because that's a hobby. And so Jamie had a hobby of working on a matrix-based solution that was going to fix this. He was largely ignored. But as we were getting towards the end, we realized that sample variance in EE that's converted by the mixing was our leading term of noise. And so Jamie really quickly took his hobby and showed that it was working, and it was very quickly incorporated into the pipeline, and the leakage has gone way down. And so the significance of our points went from a 3 sigma detection to about a 5 sigma detection right at the end. And that was a big breakthrough and one of the exclamation points on our program. After BICEP2, we wanted to, of course, get on to the Keck Array. And here are the guys in the high bay using our test cryostat this was, I guess, 4th of July, to develop detectors. And then the Keck Array's got a different design. We got rid of the liquid helium cryostats. So we have a pulse tube system. Here are people in the lab at the South Pole putting one of these guys together. And their official names are K, but their unofficial names go by the pop band The Spice Girls. I can't remember which is Ginger and which is Posh. Here's more work going on at the South Pole. And just to prove that I do work occasionally in the lab, here I am working on one of our leaky helium refrigerators. And so the Keck Array, we don't have a lot of room here in the telescope mount. Our winter rover just barely fits. And here are a couple of the receivers. But in the end, we've packed in 5 of these receivers. You can see how tight it is just with 2. And this is, I guess this was last year where we had all of the receivers out again for doing refurbishment in the lab. Okay, so here's what the Keck Array looks like when it's running. Again, this is near sunset because you can see the long shadows. There's our winter rover for scale. But one of the great things I think about our program is that across BICEP1 and BICEP2 and the Keck Array, we have a nice agreement in the signal level. And for our own internal satisfaction, it was really the concordance between all 3 measurements that convinced us that this excess is on the sky. And of course, the way BICEP1 makes a measurement is very, very different from BICEP2. And the Keck Array is also, in many respects, quite different from BICEP2 in terms of all the angles that you get simultaneously and the rotation of the focal planes. So where do we go from here? What's next? Okay, well, we heard about dust. And, well, we know there's dust. We know it's polarized. We know it's in our signal at some level. We need to measure dust accurately. And whether the level is large or small, we need to measure it accurately. I would say my own summary of the stuff you heard from Matthias is that extrapolating the Planck slides well, they have large errors, so it's not very informative. And that's why these regions have been excised by Planck. But the other thing I wanted to say is that there are extrapolations on what the level of dust is based on the total brightness of dust emission, based on, say, like the column density of neutral hydrogen. But our field wasn't chosen based on that. Our field was chosen based on the contrast, the noise variance from dust maps. So we really should be using the not NH1 as a tracer if we want to extrapolate. We should be using the variance of the dust itself. And so I'm going to make a plot. I don't have it here, but of the variance of dust versus the column density, because I think you'll see that there's huge amount of scatter in that plot, and that our fields at the bottom, I predict. I haven't made it. Anyways, the point isn't to extrapolate and to guess. I mean, we're scientists. This business of people copying slides and making estimates is getting a little out of hand. I admit we're initially guilty of it, but come on. Between Planck and BICEP2, we have everything we need to make an accurate assessment of the dust. I mean, we would have the world's best measurement of dust polarization and the world's best CMB polarimeter. And this is important, so we should work together and do it right. Matthias said, he could just wait, but of course that doesn't mean waiting for us. And the other thing that we're doing, as has been discussed, is we are busily taking data now at 95 gigahertz with the Keck Array. So we have 2 focal planes running. This is a temperature map as of a couple weeks ago, I guess. And here's the jackknife. So you can see it's basically working. I leave it for a challenge for people who want to digitize this and figure out what the polarization is. And then, this is just to show what the map looked like for BICEP. These maps are hopefully totally uninformative, but the point is that already the sensitivity of the Keck Array map is at the level of BICEP1. You haven't turned that into a power spectrum, but the data is there. And then just looking ahead a little bit to this year and next year, this is the sensitivity we have with BICEP2, 87 nanokelvin in a degree at 150 gigahertz. So this table is a progression of sensitivities. And I know it's kind of busy, but the black font is 150 gigahertz, red font's 100, and blue font's 220 gigahertz. I don't have Planck at 353 gigahertz, but that's really the best dust tracer. So the first thing you notice is that at the end of 2013, the combined sensitivity of the Keck Array and BICEP2 will be, if I've got this exactly right, I mean, there's small discrepancies, about 46 nanokelvin degree. So that's basically a factor of 2 in intensity and a factor of 4 in the power spectrum. So this is data that exists, and we're working on it. That was some of the data that went into the preliminary cross-analysis in the paper. Then this year, at the end of one season, our projected map-based sensitivity for the Keck Array at 95 gigahertz is about 150 nanokelvin degree. And you can compare that with the map-based sensitivity from BICEP1 at the end of 3 years. So this cross-spectral analysis should really get a lot better. A lot better. And then note the map-based sensitivities of BICEP1 with the map-based sensitivity of Planck in our region. What that tells you is that we have sort of a ropey cross-correlation with BICEP1, but we have a detection with using BICEP2. Well, you can do the same thing with Planck in multiple colors. I mean, that would be nice. Then for this year, we're, as I said, working on a new receiver called BICEP3. And BICEP3 is designed to have the same sensitivity that Keck has in 5 receivers at 150 gigahertz in one receiver at 95 gigahertz. So BICEP 3 will provide a huge amount of power at 95 gigahertz, which we can either use to go really deep at a 95 or perhaps we'll map more sky in the combination. But you can see here at the end of 2015, the depth of Keck Array and BICEP2 will be running around 40 nanokelvin degree. So there's more coming, definitely more. The field is also working hard on this, and we're looking forward to all the suborbital experiments weighing in. So I've mentioned our experiments, Keck Array and BICEP2, but from the ground there's also CLASS, which is an interesting experiment at Johns Hopkins. SPT-Pol, which observes our field, has already a year of data in the can. Polar Bear, which is in Chile now. EBEX is a balloon experiment that flew, might be useful for dust. Spider is our experiment, which hasn't flown yet. ABS and ion ACPOL, and then a balloon experiment called Piper. I don't know how long that's going to take. It might be a while. I mean, this is a pretty big jump that we had going from our previous upper limits down to here. And so we'll see how that goes. But we did have a big head start. Where do we go if I can look a little bit further down the road? What are the next steps? Well, Scott Dodelson wrote this paper, which is a nice paper about what he saw the steps being following BICEP2. And basically what he's saying is, step 1 is to confirm the signal. I think we all agree with that. Step 2 is to measure the amplitude of R and NS to high accuracy, to kind of percentage accuracy, which means covering more sky. And then step 3 is to measure the tensor spectrum to cosmic variance limits. And that means measuring the whole sky and having sensitivity to all multipoles. That's quite a task that Scott has set for us. In the short term, one of the ways to do that is to map more sky. So this is the Spider collaboration. I guess this was taken last year in Princeton. Note the large spider. And this is our cryostat. So Spider has 6 focal plane arrays, and it goes on a balloon, of course, around Antarctica. Unfortunately, last year, with the government shutdown, the flight didn't happen. To wage an Antarctic balloon campaign, multiple government agencies all have to be working in sync, including the NSF, the Navy, the Air National Guard. It just doesn't happen if something like the government shuts down. So that was disappointing. The cryostat, unfortunately, went on a world cruise from California to New Zealand in time for the government shutdown, and then another world cruise coming back to New Jersey. So that took a while too. Very unfortunate. But that's the team. That's the back of the t-shirts. The spider head does move. Animated spider. Okay. The other planning exercise that's going on right now is there's a DOE planning process for a stage 4 CMB experiment. What's the future for the next decade for the CMB? And well, the report itself emphasizes properly the exciting science, not only in inflation, but also on finer scales with the lensing signal. But the details are not clear, and it's really important. What's the proper balance? This picture kind of shows the two approaches. You can have a large telescope like SPT with a big throughput, or you could have a small refractor like BICEP with a huge collecting throughput. I mean, the photon collecting abilities of these two approaches is not so different. And it really comes down to what's the importance of mapping large areas of sky. What's the balance between small scale, wide field type measurements and high resolution measurements with large telescopes? And how do we develop an effective collaboration? Because we're really looking at the next stage, really is the next stage in terms of the groups involved. So it's a big question about how these disparate competing groups can be put together and melded to a common enterprise. It's happening, but it takes a while. One of the things that's going to be important is covering more sky. And I love the poll, but there is a limitation to how much sky is observable. And so maybe the way to do this is to have some kind of spinning experiment, like in Chile or in Greenland. And by spinning, you can cover a lot of the sky, and the sky just rotates overhead. This is basically some of the ideas that are in the CLASS and Groundbird telescopes. But now if the signal level of R is big, this is important. Now, I don't know if a ground-based spinner is going to work. It really hasn't been shown that it can work. But the two things I wanted to say about these future directions is, first of all, of course, I really think the small aperture approach from a technical viewpoint has been really highly successful. We've proven that we can accurately cover large areas with high fidelity, and this approach is very, very sound. The other thing I'd like to say is that DOE is not the only player here. The detectors and hardware contributions that have come from other agencies, and in particular NASA and the Department of Commerce, of all things, have been enabling, in particular in the choice of detectors and readouts. And so, that's something that should go into our future planning, certainly. And then, to measure the whole sky, we're really looking at a space approach. And I'm not just thinking of this today. I started working on concepts for a space measurement going back to 2003. This concept here is called EPIC, the inflationary probe of cosmology. And the idea was it would be a spinning experiment out at L2, like Planck, and would look back to the time of the microwave background, and over here is the epoch of inflation. Unfortunately, NASA had other ideas. So there was a news report in the Journal of the Onion about NASA's plans for the decade. And so it's been slower than I wanted. Yeah. If you read this caption, it's actually pretty funny. Well, here's what EPIC looked like. It's actually a fairly modest thing. It's a 1.4 meter telescope, but with a huge focal plane. Well, I don't know if we need that big of a focal plane. It's essentially equivalent to flying the Planck satellite 1,000 times, okay? And that's all coming from improvements in the detectors. But it's simpler than Planck. It's using a single detector technology, and it's optimized for polarization, whereas Planck was conceived of as a temperature machine, and then polarization capability was added later. But that may not be the right optimization. For a higher level of R, perhaps we can have a smaller aperture. and so, there have been many concepts that have emerged since EPIC in Europe. The latest was called PRISM in Japan, kind of a small aperture version called Lightbird. Then from Goddard, this approach called PIXI, which is both a polarimeter and absolute temperature machine. And so the challenge is, can we fit a CMB concept into the likely opportunities we're going to have in the next 10 years? And the best opportunity in the US might be an Explorer with about a $250 million cost cap. PIXI, by the way, was proposed as an Explorer in that cost cap. So I don't know. The answer is maybe. It's going to be tight. I mean, any concept is going to be a challenge to fit into that cost range. Certainly, international cooperation can help. It may be that one of these international concepts will take off, and hopefully the U.S. can be involved. There's been a lot of discussion where the field's going if we're going to go do a polarimeter. This is before the BICEP2 results, or whether, what about an absolute spectral measurement? This would be following up distortions in the background, like a phi-RAS measurement. And so, this PRISM design actually incorporated both a polarimeter and an absolute temperature measurement. And so, I think the absolute spectrum science is interesting. Coming up on the horizon here, there's actually an opportunity in Europe for a medium class mission that's due at the end of this calendar year in 2014, and then the US Explorer opportunities in 2017. I don't want to get too far ahead, but I was asked to talk about the future. Okay, so concluding thoughts. Well, I think that the next few months are going to be really interesting, and you can tell that there's a lot of data in the can with Planck and with our experiments that are going to weigh in soon. So I don't see this as waiting by any means. And I really want to see what the data tell us. That should be the goal, and that should be everyone's goal. We have to be prepared, though, after this short-term path, that the next step in experiments could be a big one. And whatever that is, whether it's a ground-based program with Department of Energy, or whether there's a space program, or whether they're coordinated, we have to be prepared for that and hopefully excited about it. And finally, I'd just like to conclude that our story is really the story of the interplay between theory and experiment. I mean, as I mentioned, if it wasn't for Mark being down the hall, we wouldn't have gotten started and gotten interested in that. And people like Mark and Matthias and Olivier and Wayne have been kind of our ambassadors to the fundamental inflation crowd, and that's been really helpful. And I'm hoping that the future here, well, I know the future in experiments is going to be great, and I'm hoping there's going to be a similar revolution in theory, because I really want to know what we can say about the early universe. So, thank you.
Thank you very much. So we have time for questions, comments.
Sorry, I'm just always asking dumb questions, but we got a nice tour of BICEP2, Leonardo and Andre and I. It was really fun. I got the impression that there's a lot of creative materials science that goes into all your choices and everything. And I don't know. I'm just kind of curious. Is there something that you're missing that would be like some breakthrough in, say, condensed matter physics or something that would be useful for what you guys do? Or is it all sort of in place now and it's just minor modifications?
Well, we're always finding things.
I mean, like the creative use of superconducting transitions is an old story, but that's like an example.
Right. Well, there's so in some cases, it's like finding out that there's a type of styrofoam that's really transparent in the millimeter waves that some people develop for housing, but as it really turns out to be good for us. I mean, there are cases of that, but in the cases of the detectors, there's really fundamental reasons why superconductivity is the detector of choice. There are developments going on beyond the transition edge sensors. So there's ways of multiplexing detectors with resonant RF tones, and that may allow us to make improvements. But we're really kind of in a Malthusian limit here with the focal planes, and they're running close to fundamental properties, and that's hard to break without just making more of them.
Any other questions or comment? Okay. If not, let's thank Jamie again.